Mine?
Yeah, verstanden. That should be on yours, I guess. This is on yours.
No.
Oscar, whose computer is this now?
Yes, it's his computer.
It's his computer. Yeah. And can you actually put it on this screen as well?
The thing, this is the connection for the beamer.
Yes.
But I don't know why the Mac doesn't work.
The Mac doesn't work.
It didn't work with my Mac Pro.
Okay.
Only with Windows.
Only with Windows.
So what I can do is I can share the Zoom screen with my laptop,
Or I can do
with
that.
or your Zoom screen with the
I can share this with the screen.
exactly.
And then we should also see the
Screen will be
this goes well.
Yeah.
Right.
I'm happy that you also have those initiatives. Yeah. Meeting Paul last week.
How do I make this big?
But I think
The laughing?
yeah, if you are quite
But I can't make this bigger.
It's probably you.
I think I see your screen, I think.
The indices of the
I see your screen. So this is what you have on your screen, I guess. So can you switch to full screen? Then it should be full screen there. Or we need to.
you need to share the entire screen.
I think the speakers screens are swapped. Yeah, that's it. Now it's done. Yeah.
Okay. Great. So we got the technology working. Last time it took us half an hour. Today it's only 10 minutes.
All right, can you hear me?
Yep.
Good. Well then, I apologize maybe for the material being part of the lecture series, but I thought in case this is of interest, and I was told that this is of interest, I can give a brief introduction of what do we do as engineers if we solve fluid dynamic PDEs with the finite volume method. And the finite volume method is in scope for the project. So this is part of a lecture series, and I might go back to this. It's hard to see for you here. So to this part, which is convection diffusion, this is actually the core problem of fluid dynamics. And the PDEs, of course, in here, sources, transient changes, etc. And then how to do this with finite volumes. Okay, so let's get started. How do we do? What are we looking at? We're looking at, in green, what we call the strong form of the PDEs in a residual form. So everything is pushed to the right-hand side, and we have a transient term, a convective term, a diffusive term, which might be heat conduction or might be viscous shear stress or fixed diffusion, and a source term, which is everything that doesn't fit the first three terms is dumped into the source term. And in continuum physics, you just gather all these equations for the various phis. Phi equal 1 is the mass equation, phi equal the velocity vector is momentum according to Newton's translational momentum. Angular momentum is irrelevant, so to say, for fluid mechanics if you have the proper material law for the shear stresses, heat capacity times temperature is some sort of internal energy as we look at it. And you take this green equation and you plug it into a weighted residual method where W is any weight that can vary in space and time. And of course, if something is zero, then the integral of all these zeros in different points of your domain is zero. You can go subdomains, you can go subdomains in space and time. And you're essentially only adding up or integrating zeros, which you can also weight. And then the difference is what kind of weight do you choose? And if your weight is 1, you call this the finite volume method. If your weight is the Dirac function, you call this the finite difference method. This is actually some sort of gambling trick because the delta Dirac function essentially doesn't do anything else but through some magic erase your integral. So you're back to the strong form, the green part. And if your weighting function is the ansatz or shape function, which sounds a bit bizarre now at this point of the lecture, this is called the finite element method, which has advantages, in particular, if more than second derivatives occur. This is the case if you staple equations, you can, for instance, for a beam mechanics, you can use two equations. One governs the momentum of this beam, one governs the forces, and if you plug one equation into the other equation, 2 second-order derivative PDEs are merged into 1 fourth-order derivative PDE, and then actually it's more advantageous to use the finite element method because integration parts, which we'll see in a minute, can be executed much more often.
Can I just ask, this delta function choice is
Finite differences.
finite differences, but you choose the delta functions at kind of which points
Okay.
to have
Where do
these?
you choose these delta functions? Actually, these delta functions, you choose them at your base point or support points of your grid,
Okay.
which then basically erases this integral and gives you a
Just
sequence
some.
of, say, a finite sequence of individual PDEs in strong form at your base points. So the delta Dirac function then is imposed at your supporting points of your point. Okay, so I just copied it. This is the strong form, and this is the argument probably all of you have seen multiple times. Essentially, if this is 0, the sum of all zeros is 0, and the sum of zeros weighted by some other funny function is also 0. This is called the weak form. Essentially, the residual doesn't need to be 0 at all points that you track, but on average, with some kind of funny weight, it's 0. And that's why it's called the weak form. So the residual is not 0 as indicated here at all points, but only on average. And this weak form has a number of benefits. If you go to what Dieter just addressed is, now what do you do with that? You have to discretize that. So far, this is still a continuous form. You have to bring it to the computer, then you have to discretize that. We use ansatz functions. Ansatz functions can be global or local. And typically, as in everyone else, we use local ansatz functions, which have a local support, as indicated here by the red line, as compared to the light blue line, global ansatz functions, which are much more challenging in terms of complex boundary conditions. Complex boundary conditions are one of the crucial things for engineering. And with global ansatz functions, such as a Fourier decomposition or some kind of other global ansatz functions, you usually run in trouble if you have to meet complex boundary conditions. Okay, so we use these local ansatz functions as supported by a number of points. Locally, in this case, I think 5 are marked, and you can use Lagrange polynomials, which only consider the value of your dependent variable at that point, or you can consider Hermitian polynomials, which might consider derivatives of curvatures. This is some sort of compact differencing, people call this, because the order of your ansatz function increases with the amount of information that you plug in. And if your information does not only inherit the value, but also the gradient or the curvature, you're getting higher order ansatz functions at more compact domains. Okay, so actually in finite volumes, gradients are often also used to reconstruct higher order ansatz functions. But so far, we say we only use Lagrangian polynomials that only base on the function. We will introduce the gradients later on. Yes, we won't do that today. And mind that these functions can be, for instance, linear polynomials as the red lines, and higher order, say, parabolas, as indicated by the blue lines. And actually, at the same point, we use different ansatz functions. That's an important principle. From a mathematical point of view, you might say the guy is crazy. He uses second order here and linear at the same time. So he shoots himself in the foot, since the linear ansatz function is then setting the point for the accuracy. But there are reasons which come from physics, which motivate it, and you can actually prove that they go down to the algebraic system that you saw, to use a hybrid mixture of ansatz functions at the same point.
Can I just ask why the difference between Lagrange polynomials only referring to grid point values and Hermitian polynomials to also derivatives? Can't you do each with both depending on which?
Well, from what I know, a Lagrange polynomial only uses the function, and the Hermitian polynomial in general, it depends a bit on the definition, uses derivatives, whatever kind of derivatives you have. And all of them are extracted at your support point because we only have information at the support points.
Right, but all of these polynomials can be chosen to different orders.
They can all be chosen to different. It's up to you to choose them to different, or you can mix them violently.
Right. Okay. Yes.
Which might be questioned in terms of the algorithmic complexity, well, not in terms of the complexity that you count, but the complexity of the guy who needs to code this and manage it. But you can basically violently mix that, and some people do.
And so just for me to get my head around this, so if you choose Lagrange polynomials, you work out the prefactors in front of the different powers of x from the grid points themselves. And for the Hermite polynomials, you need the derivatives.
You need the derivatives, and you work out the accuracy with also the powers of x, but
right.
As the derivatives, if you do a Taylor series,
right,
you might have terms like f in a location is f at your base point plus f dash at your base point delta x plus delta x squared, blah, blah, blah.
Yes.
Now, if this is your unknown,
okay,
actually this is known. So you are one order better.
right.
You don't need to make sure that this vanishes or gives you already a first error, because you know this as part of your unknown.
Okay.
Okay.
And do you need some consistency with mixing these different ansatzes, or is this?
Well, consistency is an issue in terms of, we will see that in a minute, the values that you get at certain phases where fluxes, we call it, or information is transferred from one, say, element, grossly speaking, to the next element. And their inconsistencies can be an issue, or consistencies are an issue.
Right.
Okay. Okay, so what is the big benefit of the finite volume method, or choosing the weight to be one in the weighted residual method? The big benefit is, as we'll see in a minute, that input and output are inherently linked to each other. So you can guarantee by very simple things in your code that what comes in a duct as a mass leaves the duct as the mass. And find that this is by no means guaranteed with the finite difference or finite element method. And if the mass fluctuates for some funny reason that, you know, is an issue which pops up if W is not 1, then with the fluctuation of the mass, your momentum can fluctuate, your energy, so you lose control over the properties which can be crucial, or is usually very crucial. Now, this input-output relation is often called conservation. So this is a property that comes with a method. You cannot spoil, violate, torpedo this. Well, you could if you do the coding wrong, but essentially you only need to make sure, this is what you mean by consistency, that what you compute here for the first control volume leaving at that point is exactly the same value that enters the second one, but with another sign. So this is out and this is in, which means you don't algorithmically go from control volume to control volume to control volume, but you basically introduced already a phase-based data structure. You go from phase to phase to phase to phase to phase. And for each phase, you consistency, which means only once, compute the flux that crosses the phase. And then you add this number to that control volume and subtract it from that. Okay, so this is what you mean by consistency.
Yes.
If you would go algorithmically from here and then do this, and then you compute this for some reason due to accuracies of the machine twice, but different, you lose all the power of the method. So it's a phase-based data structure, usually, or not usually, always. Which brings me to discretization. The left shows finite differences for a simple sort of expansion flow. So you come from the left, you leave somewhere in the right, and usually what you do in finite differences, you draw funny lines, and along these lines, you distribute points. And if you're lucky, it comes structured. So you have lines I, J, K, which do not cross each other. I does never cross other I lines, crosses only J and K lines. In finite differences, you can actually use the same mesh, but for some reason, these base points, support points of your ansatz functions are somewhere in the middle of what we call a control volume. Other people call this an element, whatever, you could call it anything. Now, you discretize the domain, therefore, in terms of these control volumes, and these control volumes can have an arbitrary shape. Since you have a phase-based data structure, they usually have a polyhedral arbitrary shape. They look like footballs. Okay? The important thing is there is no gap in between. They have to fill the whole domain somehow, which is easy to do if you're not restricted, like what you're typically in many finite element methods, to certain type of elements. In finite volumes, you usually are not restricted to hexahedrals, tetrahedrals. You can do any hedra, poly something, and you just cluster them together, whatever they look like at the end. Thereby, you're very flexible with filling the individual, very complex engineering domains. Okay? Good. Now, to go to the details and outline the details of the various discretizations, say we have a number of points, okay? And now we spend grid lines. This is called the finite difference method or discretization. But then we can draw these funny dots around it. Now, in this case, this is called the cell-centered finite volume method. Why? Because these bullets are exactly in the center of these polyhedral, in this case, quads. So if you have a polyhedral, you actually put the point exactly in the center of that point. You can also do it like that. There are people who do it like that. Now, what is the difference between this and that? The difference is that here, the faces separating these control volumes are centered in between the points, okay? This is called the cell vertex or face-centered scheme, is another option. To be honest, in practice, this has no meaning. Everyone who goes for practical simulations does it like that. And there is a reason which I'm trying to outline now. Now, this is tempting to make a long story short for the midpoint rule of differentiation. The midpoint rule of differentiation says to have a parabola, then if you have 2 points and a control volume, the tangent to the center is exactly to the difference quotient between the components. Okay, so this is exact. If you are not in the center, this is of course not exact. Okay, so this is the midpoint rule of differentiation. The midpoint rule of differentiation occurs actually for the diffusion term at the faces, which means this term is second order accurate in this location, but not here or there. There's another rule, as we are forced to solve integrals, we have to take care of how to integrate in space over areas or volumes. The other midpoint rule says that if you want to integrate, over a domain, then you take the value in the center times the size of the domain, and you are able to do linear functions accurately, which means it's a second order accurate method, because there are two triangles which are congruent. One is too much, one is not, is missed. That doesn't work if you evaluate somewhere here, because the triangle you get here is far smaller than the triangle you get there. Okay, so this is the midpoint rule of integration, and this actually would recommend to store the data like this. So you can either do this rule or that rule. It's up to you, you decide, but I would recommend to use this rule. Why? And this is what most people do. First of all, you're making integrals, as outlined there, second order accurate with only one base point. People call this Gauss point in finite LMS. So it's a smart way, only one unknown, but second order accurate. Of course, you could do more unknowns, higher order accuracy, but mind that we have a phase-based metric. So we know the phase, and our unknowns are phase-based oriented. All vectors are oriented across, something that counts the phases. And for a phase in a polyhedral arrangement, it will be really, really challenging. If you have a phase, you have a polyhedral, and the next one looks like that, and the next one can be like this, and this one looks like that, and this like that. Now my point is, if you're somewhere here, you might know I belong to this control volume and that control volume, because that's a unique thing. A phase can only be owned by two neighboring control volumes. But what you don't know is what is the next one. This is really challenging. And actually, we don't know in industrial engineering. You know that in finite elements because you have a restriction on the amount of elements that you have. You can have maybe only hex or hex plus 10. But as we have polyhedrals, this actually is our price we have to pay. We don't know anything about the one but next neighbors. These things are not known.
Sorry, one question. So from what you draw here, it's clear that if you have a kind of rectangle like here, you can put it into center. Is this possible for any kind of different shape that you use? That
for any shape, I know the center.
You know the center, and if you
put it there, you're second order accurate for integration.
For integration in all directions.
Yes.
Okay, and that's the center of mass.
That's well, it's not the center of mass; it's the center of volume if the mass is homogeneous, or if the density is homogeneous. Okay. But as a chip, I would say there is a difference, of buoyancy of chips. So this is actually the rule that we prefer. This is the rule that occurs there. And what is the next benefit? And this is a hidden tiger. You won't find it in textbooks, but everyone in practice tells you that this is actually the driver, another driver, and for most people, the driver of using this metric in terms of cell-centered versus phase-centered. These points in light 3D gray-ish never occur in your calculation system. Now, why is that important? And we'll see in a minute, they do occur in the other structure, data structure. I say this is the rear of an airfoil, the trailing edge of an airfoil, okay? and say you would like to heat the trailing edge of the airfoil, okay? And you have control over the upper side and the lower side temperature, okay? Now, what is the temperature at this point? You don't know. And these funny things occur in practice a million times, and you are really, really bothered by that. And you have to do really complex structures in your algorithm and design your problem around these structures. And that's actually a pain. So as we have more than enough trouble with other things, I would recommend not to increase trouble where you can avoid trouble. And these points actually vanish automatically if you do the cell-centered scheme. In the node-centered scheme, you see that you generate basically half control volumes in the border, and then you have fluxes across these borders of these half, which come from that point, and therefore this funny point occurs. And you need to be aware of the trouble you are introducing there. On the other hand, as already outlined before, derivatives at the center of, at the face are one order of accuracy better with that rule because the midpoint rule of differentiation applies. Okay, so far so good. So we have the domain, we fill the domain with polyhedrals, we locate in the center our points. And then we use that as a discrete version to do this equation. Before we go to the numerics using the discretization, we do some steps in between. And the steps in between are we collect the terms that adhere the gradient or the divergence in this case. And you have that here and you have that there for convection diffusion, which together work out as what we call the fluxes, because they both have the divergence in front. So we take these terms and collect them here, and then we do a non-numerical thing. We convert this volume integral into a surface integral using Gauss theorem or integrating by parts once. Now, these surface integrals represent fluxes. What is the benefit? We get rid of one derivative. The derivative is gone. What is the problem? We now have integrals over volume and integrals over faces, so that might sound like apples and pears to some people, and we have to add that. And we have to think of what does that mean for the discretization. And here's the trouble. You always, there's no such thing like a free meal. The trouble is that in terms of your discretization, you have to think of ansatz functions because the discretization doesn't continue to the faces. Okay, so I've said that. The challenge is if you discretize these surface integrals, you need information somewhere here, which is not where you have the information according to your discretization. And this brings in the funny shape functions, ansatz functions, whatever they're called. Okay, so how do you do this? Actually, you use this midpoint rule for both, for the volume and the surface integral. And the midpoint rule says you take the value in the center, you multiply that with your domain size, might be a volume, might be a length, might be a surface, and that's it. So you go into the center of the faces and you multiply that with this face. Up front, of course, this is a closed surface integral around your football. You structure that into a sequence of subintegrals. Each of these subintegrals here is one of these patches, which then is represented by the center of that patch. Okay, so instead of running around, you do this plus this, etc. But you have to gather information at the green points, and this is actually where you don't have information. If you want to discretize this, you do whatever you do. I mean, I think the slides do first Euler backward, which is the most simple one you can do, but you can also think of more complex ones. You take the information in the center of your control point now, yesterday, the day before yesterday, which gives you the discrete version of the time derivative. You multiply this with the control volume and then that second order accurate. So this is sketched here. You take the value in the center times the control volume. If this value in here is a derivative in time, you do the time derivative at that location for different time steps. Good. For the surface integrals, as I said, you do the same rule. You walk along the surface and you grab the different center location values, if you have them. If you don't have them, you need to reconstruct them in some way. And then you just multiply with the surface vector. In this case, it's a vector information. So it's vector times vector. Okay. So far, so good. Then you need all these vectors, which comes from a mesh generator. This is no issue. People have that. And then you approximate the subintegrals by the midpoint rule. We have done the midpoint rule. It's not too complicated. You have these congruent triangles. But in this case, the problem is you don't have information where you need it. You need the information there. And now, where do you get that information from? First of all, information is needed for two terms. One was convection, one was diffusion. Both of them inherit the divergence. And now comes the fact that in the same algorithm, at the same point, but for different phenomena, convection or diffusion, you use different Ansatzfunction, which might be questioned from a math point of view because different Ansatzfunction might create different orders of accuracy, but the physics is different, okay? Now, convective physics means directed physics. It's like time. You would never try to reconstruct a time information for now from the future. That doesn't work. The future doesn't, well, apart from stock market, the future does never determine the present. So things go parabolically from past over present to future. The same happens for convection, the message in a bottle. If you throw the bottle in the river here, you can communicate to guys in Cuxhaven, but not to guys in Dresden. They will never be able to get your bottle. Okay? So there's a directional information. It's a one-sided, say, approximation, which in this case is not fixed, but goes with the direction of the flow that can vary, of course, in space and time. And that's why the reconstruction also needs to look upstream and cannot pick downstream points. It cannot be a linear polynomial which involves downstream and upstream to the same weight. That's stupid for convection. For diffusion, the thing is different. Diffusion is our, say, engineering approach to molecular branch motion, which is statistically averaged. And we use whatever viscosity, heat conduction as a property that represents a huge amount of molecules that exchange their properties. So this is actually inherently symmetric approach, which means if you discretize that, you have to take an equal amount from the left and the right, from the top and the bottom, etc. So there's no way you can prefer information from one side or the other, which means actually these shapes and these shapes look different, and therefore they might also be of different order of accuracy at some point. Why? Because to be second order accurate here, you actually need this, that, and the next one, and you don't know the next one. They're unknown in arbitrary polyhedrals, which essentially brings some sort of accuracy issue into the convection diffusion problem. Okay.
So can I just ask, what makes the kind of...
I see that many people don't understand, no, so I'm happy for someone to ask.
So what is the advantage of splitting the integral up into a surface integral into a volume integral in the first place. So if you did just work out the extra derivative and then just use the integration method, how do I see that this would be less accurate?
Well, okay, this example actually to some extent shows that in terms of accuracy, it can be doubted where you actually lose something and where you gain something. Formally, you have one derivative which is no longer there. There was a derivative here,
Yes.
and there's no derivative there. So the amount of derivatives that you need to worry about is an order lower. There's no derivative here, you just extract the values and you only have a first derivative there. However, the way you treat these terms basically boils down to something which is at the end of the slide set. I'm not sure whether we have enough time today to do this. Shows that if you do finite differences, and that's essentially you are not able to get rid of these derivatives. If you do finite differences, you don't have the integral in front, then you can't do else, you can't do integration by parts. You arrive at exactly the same, well, not exactly, virtually the same formula, if you apply the same principles. So what you do then is you work out an approximation for the gradient, thinking of that if you want to have the gradient of a curve, you cannot go downstream because downstream cannot, determine upstream. You have to go point itself and upstream. Okay? Whereas for diffusion, it's a second derivative. What is the second derivative for symmetric finite differencing? It's the point itself, one to the left, one to the right, gives you a parabola, which gives you second order accuracy for a centered scheme. And essentially, the matrix that you derive from doing this and doing that is the same virtually. I would say we see there are small differences, but there's a 1 over delta x, or delta x as a factor, or 1 over delta x as a factor, which connects the two. Okay, so there's no substantial difference. The nitty-gritty detail is that in finite differencing, you're not able to match this. What comes in goes out.
Yes.
Why? Because all these properties are no longer phase-based properties, but they will be properties in the center of the control volume. Okay, so what happens if you evaluate a term here and a term there? There's no guarantee that they agree.
Yes.
And if they don't agree, you don't have this input-output thing. So basically, apart from the factor delta x, they distinguish in the way you evaluate these tiny terms. Where do you evaluate them? How do you reconstruct them? But in principle, the matrix in here is the same components. Okay?
Okay, understand.
So the benefit is actually that you guarantee this conservation, which is.
So this would not be possible in the volume integral. You could not, because you would not know what the flow is. Okay.
In the phase, you actually guarantee that you come in through a phase, and whatever goes through the system, at the end of the day, it has to go out. Why? Yeah. Because each phase is connected to a neighbor, and nothing can get lost.
And so you would do that for any term that it might appear that has a derivative with respect to space.
You do this.
You do this always. Okay.
This is absolutely crucial.
Okay.
Yeah. Where have we been? I think somewhere here. Now we have two terms. One is convection, one is diffusion. This one, convection, is oriented. You have to take the information from upstream. You are not supposed to take information from downstream because that cannot govern, as the message in a bottle. If someone puts a bucket with whatever ink into the river in Cuxhaven, we will not be able to realize this. You won't see the ink.
But can I just ask, so you don't need here really take a derivative anymore?
Well, that's true. Well, here, but,
Here you need, but not there. So that means that,
but the thing is that you have to evaluate it now
at that
at
point,
that
okay.
point where you don't have information.
right? Yeah, okay.
So the question actually boils down to, in finite differencing, you have the finite difference at that point. And then you have to take this point and that point. And here you have the value here, which if the flow comes from here, you have to take it from there and not from there. And then in 1D, very simple. How does that work? Imagine you have a 1D control volume. Now, this actually boils down to two phases in 1D, which means for this one, if the flow comes from here, you take that one. But you also have the closed surface integral also has this phase. And for this phase, you would take that one, which means the total approximation involves these two, one for that, one for that. If you do finite differencing, you actually would do the same thing. You take the finite difference between the, du dx is this minus that, not that, because that's downstream. So actually, that's why I'm saying the matrix looks the same. And here's the same ingredients.
Right.
The matrix, you would get a matrix.
That point is include most of the information. So
This point is used to get the information here in finite volumes. This point is used to get convective information here in finite volumes. In finite difference, you would have du dx, which is this minus that. If the information, if the flow comes from there, it would be this minus that if the flow comes from there.
Okay, so do I understand this then correctly? When you want to get this green, the information at the green points, you always need to work out in which direction is the flow going.
Yes.
And once you know that, you determine
Yes.
whether you take one value or the other.
Yes. And we'll see that here in a minute. Now what you want is delta A times the velocity times phi times rho. That's a convective term. You group that into two groups. One group is rho is not yellow, not indication. Rho should be in yellow, which is called the mass flux. The mass flux is your skateboard, which you use to surf through the face. The skateboard is linearly interpolated, okay? But the question is, who is riding your skateboard? Who serves on that skateboard? And this is the guy phi f, and the phi f is actually used using some kind of, does the skateboard come from here or from there? Which information is going on your skateboard, basically? Okay, so to do this, you actually say that you have a piecewise linear constant. So this value goes to here, this to there, if the flow comes from here. If the flow comes from the other side, this value goes to there, this to there, and this to here. How do you do these piecewise linear constants? That's simple. You basically, let me see, where do I have that? No, it doesn't come, huh? Well, I can do it on the whiteboard. You basically get some sort of algorithmic switch. Max of m dot f 0 times phi p. If this is your control volume, and you usually say p is my center point, and this is my phase f, and this is the neighbor, whatever this neighbor is called, or the east or whatever. plus. Well, plus gets minus because we usually also take max, but this is a matter of taste. M dot F negative 0 by neighbor. So if the mass flux is positive, you're taking this point in that location. This is phi F times M dot F is equal to. If the mass flux is negative, you have to take this point. Then minus F, well, minus mass flux is bigger than 0, but you reverse the minus here again with that minus to get the correct flux sign, and you're multiplying with the neighbor value. So this is some sort of simple bridge, which is essentially a piecewise constant profile, which essentially is second order accurate because you have one here, one there. So you have 2 points which are involved to get the total integral.
So this may be a really stupid question, but how, if you have flow that now flows into a volume, I mean, can there be any, can you?
Can't see because you would compress.
Compress.
flow.
Yeah,
Then you actually, well, you could do that because you execute the same rule.
yeah,
There's no issue.
okay,
The only thing you have is you have a lot of mass that enters and the mass cannot vanish.
yeah, so you
So
get,
the only thing that can happen is you change the density
okay,
for some funny reason
yes,
in
impressive,
compressive, not incompressible,
Yeah.
but incompressible flows. And this can happen because in compressible flows, you have, it essentially says d rho by dt, that's the term you're hunting for now,
yes,
plus d rho by dxk, uk is equal to rho dk by dxk. And even if that wouldn't count, we would have here the divergence of the velocity. So basically the change of the density is paid by the change of the volume, or which can expand or compress or whatever.
okay, so this means this upwind can never lead to any inconsistencies.
No.
No.
And I won't be able to do it today, but if you are, we have slides for that, I can circulate. It's very simple to show. If you go for upwind, the matrix properties in terms of the condition of the matrix will always be beneficial.
Okay,
So that's why the part that enters the matrix, we call the implicit part of the equation system of the algorithm, is always upwind biased. Whatever you do, you can hunt for higher order accuracies, which all of us do. But the higher order accuracies will never go through the matrix, always through the right-hand side. Why is that? Because the system is inherently nonlinear. So we will have nonlinearities that enter the matrix, which have to be linearized. So we have to iterate anyway. There's no way we can avoid that. And then we can also accept that we have to iterate due to the high order accuracy. But the matrix is always favorable. And there are 2 rules which govern from a physical point of view, these matrix rules. And actually you can see that they boil down to upwind to some extent.
okay,
The rules are, first of all, monotonicity. So if you have a function and you want to know the function here. Numerically, you are actually looking for a value that is thresholded in between the neighbor values. People call this monotonicity. So a scheme that doesn't predict this over or undershoots is called monotonicity preserving. which means you don't allow the first derivative to change sign. Essentially, you can go like that, or you can go like that. That's okay, but not over or undershoot because you introduce severe oscillations. Now, if you want to have a monotonicity preserving scheme, it tells you basically that the coefficients of your, well, all your polynomials will move into a matrix, and the matrix coefficients, depending on whether you put them to the left or the right-hand side, have a certain sign. Okay, the sign is fixed. Otherwise, you have monotonicity trouble. And there are many approximations to introduce monotonicity problems, but there are, strictly speaking, one of the reasons for it is we don't have that. Okay. The other thing is the most simple physics that you have is homogeneous physics, homogeneous temperature. Now, in a simple approach, where you don't have strong sources that eat up mass, you extract oil from a pipe or put in or whatever. If you don't have these strong sources, actually you're not able to do the very simple homogeneous temperature distribution if for some reason you do things that would exactly torpedo this upwind idea. So you can show that you're not able to do this. The matrix will look really funny and is not able to do even the most simplest problem. Okay, so the second term was the diffusion term. For the diffusion term, it's actually very simple. Diffusion is symmetric. So if I'm somewhere in the phase, I'm supposed to take information from the left and from the right, or 2 points from the left, 2 from the right, or 3 from the left, 3 from the right, but not unbiased. Okay, the most simple one is 1 from the left, 1 from the right. As I said, we don't know the other ones anyway, which is a bit of a trouble because, well, you might say the order of accuracy is spoiled since this is not centered. If it is centered, the order of accuracy is better. But why do we discard that? This term is the diffusion. Those who are familiar with fluid mechanics has a number of similitude parameters. Reynolds number, Froude number, whatever kind of Mach number, blah, blah, blah number. Strohal number, they come from a similar analysis. And the biggest influence is the Reynolds number. The Reynolds number is the number in front of this term. Okay, so if you work out everything non-dimensionally, you have 1 over Reynolds actually in front of this term. In engineering, the Reynolds number is proportional to 1 over viscosity. Viscosity is for water 10 to the minus 6, kinematic viscosity, not dynamic, and for air 10 to the minus 5, so a very small number. For any other working fluids in technical problems, also usually very small, okay? If you don't do honey flows at very low speeds, the message is the Reynolds number is very big. Now, it's velocity times length divided by the viscosity. The velocity in engineering is usually at least a meter per second or more. I mean, if you drive a car, it's maybe 10. If you fly an aircraft, it's even more. If you run a train, it's more. The length, well, it depends on what your reference length is, but usually people take some sort of external length of your device. The length of your device is never like that. It's usually like this or bigger. So the Reynolds number is usually 10 to the 8. And 10 to the 8 means you divide this term by 10 to the 8 as compared to the other terms. So if you think back of the initial equation, the residual equation contains 4 terms. One of them goes in as regards or compared to the others with a penalty of 10 to the minus 8. Now, how much effort would you devote to this term, really? I mean, you can cancel it and you won't see it. Sometimes people say that. This is why I don't care how accurate this is. But formally, okay, but practically speaking, you wouldn't really devote too much effort to it.
But you can't just neglect it.
You can't neglect it because many phenomena hinge on that term, are triggered by that term. But you would not see the effort you put in there. I mean, we did something on top of that. If you put in more effort here, you can do fourth order accurate, say in structured grids. But then you need to do fourth order accurate finite volume integration. Upfront, you have an integration also. And believe me, we did that, you don't see it. You see it in other terms, but you don't see it in this term. So you see it in other terms, which is you actually see it if the Reynolds number is big, the convection dominates. You see it in this convective term. So actually for this term, it makes a lot of difference whether you reconstruct the flux this way or with very funny high order polynomials. Numerically or mathematically, you would say this is nonsense because you had an integration up front. The integration is a midpoint rule, is second order accurate. You can never be better than second order. Why do you do fifth order reconstructions? You will not be able to see that formally. True, but the term is crucial, is very important, is augmented with the Reynolds number, if you want to have it like that. And that's why this pays off. Everyone does it in practice, although the integration is always second order accurate. Yeah, so this is very simple. You have a normal vector times the gradient, which is d phi by dn, which in 1D is simple. It's actually phi left minus phi right divided by the distance in 1D. The thing gets a bit tricky if you're looking at, but we will not be able to do it now. I think I should stop now. Not
No,
the thing gets a bit.
I could listen to you for hours.
The thing gets a bit tricky. Still, you know, the thing gets a bit tricky. These are the cell centers for this arrangement. It's a simple 2D thing. Now the distance goes like that. The normal goes like that. This is a problem. This is a problem which immediately pops up as soon as you leave 1D. And it's no longer this minus that divided by distance. And there is a severe problem in terms of the angle here, which is called the non-orthogonality issue. So actually what people do is they already have trouble in reconstructing the value there because they use, as they only know 2 points, they use a linear interpolation. We don't, you know, if this is my face, I only know the 2 neighboring control volumes with their centroids. I don't know the others, which means actually your interpolation is giving you a value somewhere there, wherever that is. This value is not even part of this. And then you can actually also try to interpolate the gradient. That was my sign for the gradient from here to there. And if you have the gradient here and the value there, you can shoot into this point. But mind, this is explicit. This is actually not interpolating, but extrapolating. This final step would be extrapolating. Extrapolating actually inherently, I wiped it out, means that your monotonicity is no longer preserved. It's very simple to see if you have something like this, a value here, a value there, and you would extrapolate to your face, but you might have a value here. So this would be your curve, but your extrapolation will immediately leave, of course, over and undershoots. So monotonicity is gone as soon as you play this second order extrapolation tricks, which is why I'm not too much recommending such things. But mind that, you know, this simple thing doesn't work for even the very trivial 2D rapid. Doesn't work. So what people do is they save the matrix. They say, well, for the matrix, it's very good if I have left minus right divided by distance. Though we see this has nothing to do with the directional gradient in the normal there. And then we say, this is what I wish to have. I put that in the matrix. And on the right-hand side, I actually use what I have. This is the normal. Minus the wish. The wish is actually gradient times d minus d. D is this. So actually it's wishful thinking plus reality minus wishful thinking. Okay, this is some sort of left-right pocket thing, but This is the matrix. The matrix has really good properties then, is stable. This is the right-hand side. The right-hand side, we don't care how the right-hand side looks, can be really dirty. If you would put this to the right-hand side, you actually might risk that you lose the main diagonal on the right-hand side. This is essentially the message. You might lose the main diagonal on the right-hand side. And the matrix is usually asked to be dominant by the main diagonal. If that's no longer the case, you might have severe trouble to iterate to convergence. It will not be working. So to save the matrix, we do this, and then we put that to the right-hand side. And that's actually everything for today. This few slides, they execute this concept for a simple 1D flow. For 1D flow, you only have the east and west face, two faces. And then they collect and do that for time derivative. First order, this is extracted here for this. And we go to the next term, which is the diffusion term, east minus west. This minus this gives this. And then we go to the convection, which is essentially take the flux here and the flux there. If the flux goes positive, we take this here and this there. This actually, although this is minus, gets a negative sign, east minus west. And then if you sort amongst the entries for this, the entries for that, and the entries for that, you sort them, you're getting the unknown vector and the matrix entries. So you sort them, phi p times this is your main diagonal. Phi west times this is the other off diagonal, and this for the east, and this is the right hand side. Okay? So what you see is actually that the sum of this is that. You see that? This is how to guarantee that you can do homogeneous temperature distribution. Otherwise, you won't be able to do homogeneous temperature distribution. If they are not equal, if this plus this is not that, then this is actually bigger or equal to that in terms of the size. And then there is a transient term which augments the main diagonal. It's very good for your numerics. And you actually have flux consistency. Okay. Now you do the same thing for finite differencing. And this happens for finite differences. And if you compare the two, they actually, that's what we discussed, they look fairly similar.
Yes.
But the difference is, where do you evaluate these properties? And if you don't evaluate them in the faces, you don't guarantee that this is conservative. And you can see that in a simple example. Say we have 5 controllable, no, 6, 4 of them interior, 2 boundaries. And I just take the equation here, this one, and the one below, which is the discretized version. And I write that up for number 2, number 3, number 4. Okay? And now let's see what happens if I sum them all up. If I sum them all up, this is also a valid discretization. And if I sum them all up, my aim would be that what I plug in, this is one big control volume, should be what I get out naturally. Disregarding of how many things I put in the middle and how I do that, this should always be the guaranteed. And if I just sum them up, you can see that actually, where's my stick? East 2, number 2 east is here. West 3, that's the same. Okay, so east 2 and west 3 times 3, phi 3. You see that? If I add them, just neutralize. And you find many terms which just neutralize each other. They just neutralize each other. So at the end of the day, you just erase them. And if you just add the thing, you see that input is output, basically. It basically says that whatever you do inside, this is always that. Okay? And that's actually very crucial because you can do that for mass, and with the mass, you carry momentum, you carry energy, you carry whatever. And that's why the method is so much appreciated by engineers. I think I should stop. I have a slide which goes for high order convection, how to do that, but it's actually done along this wishful thinking plus, the real deal minus wishful thinking. It's called the deferred correction approach in numerics, and something which we do very often in many terms at many locations of the code. And it's a very simple thing. Okay.
All right. Thank you very much. I think I should ask if there are questions here.
Maybe just one basic question. So I didn't really understand what.
And online?
This monotonicity. Why was the monotonicity equation important?
Why?
Yeah.
Because if you actually introduce new extreme values, that's done by not considering the monotonicity, you would introduce oscillations to your iterative scheme. And you don't want to iterate on these oscillations because you have more than enough to do to iterate to a real solution. In case the accuracy is insufficient, I would recommend to put in more points, more unknowns, more elements, or to make sure that your approximation can be higher order, but doesn't have the disadvantage of introducing new extreme values, which will cause oscillations to the system. And what people do is they use what I use as the Hermitian polynomials. So instead of only the functions, you also have the gradients. Why do you do this? Because you only know the nearest neighbor. And that means you are limited in terms of the polynomial accuracy that you can introduce if you have a very compact domain. And then you take the nearest neighbor and its gradient to reconstruct a higher order polynomial, which can have, if it is some sort of parabola, overshoots or undershoots. But then there are monotonicity preserving, say, filters or tricks that are supplemented to this approach. And it's called the total variation diminishing or normalized variable, something. They all do the same thing. From my point of view, they just cut these peaks. Okay, so they clip them.
So can one say that if you get additional minima or maxima, you've essentially violated the sampling theorem, like with sampling theorem, and that's never a good thing?
I'm not too sure whether I know the sampling theory well enough, but I would speculate yes, because in many occasions I realized that these theorems get in trouble if you have these funny over and undershoots.
Yes.
And as a matter of fact, everyone then, if he goes for higher order, has these funny, scissor elements which basically clip over and undershoots.
Yes.
I have a very simple question. Can you comment a bit on the computational complexity of the different schemes that you mentioned about the difference?
I think they are very similar. They're very similar, not orders of magnitude, away. There is a new approach which is called discontinuous Galerkin, whatever, which elaborates more on. We actually do one partial integration by part step. They do several, which can be different because their strategy is basically to align as much as possible unknowns locally, which has advantages if you go for high performance computers, which typically have problems with the data structure that can be violent. And if you need information from remote locations, you're usually done there. And there, the complexity also changes. But grossly speaking, there's no big difference. And the finite difference and the finite volume schemes are actually, because, the thing I showed the slides before, they look basically the same. It's just 1 over delta x, which differences them and the way they evaluate these phase-based or node-based properties.
So the biggest advantage is that you can adapt to the geometry of the domain that
Actually, people say that, and that's true, that the finite volume method is very good if you have very complex geometries because you can have arbitrary polyhedrals which you squeeze in here. If you do some kind of least square based approach, which I can outline whatever sometime later, you can do basically the same thing with finite differences. So I know that many books say this is much more flexible geometrically, but honestly speaking, it's not true. Strictly speaking, not true. I would say the conservation property is actually a very good property, which I wouldn't give away if I have the choice. Because if you look at some sort of least square methods, what do they do? You know, if you have a finite difference stencil, and you have to evaluate d by dx. Okay, even in 1D, you can do d by dx with the left and the right. So it's overdetermined. You have one unknown, d by dx, but you have two options. Or maybe another, you know, even more options. And in 3D, what is the smallest element? You have a tetrahedral, which is one there, one there, one there. In 2D, sorry, a triangle, one there, one there, one there. Two gradients, 3 points. 3D smallest element is this tetrahedral, 4 points, but only 3 components. So, and polyhedrals, you have 20 neighbors for 3 components. So it's heavily overdetermined, but you can actually use some kind of least square approach. You just multiply with the transposed of this ansatz function matrix, and that's not too far away from a finite volume scheme, to be honest, if you do that in finite difference. But all conservation aspects are no longer guaranteed, and you can quickly show that they are gone. And I wouldn't give them away if I'm not, you know, forced.
But now, as you mentioned, it's overdetermined, so we have more constraints than the number of variables, right?
That's the way you construct it. You don't need to construct it like that, but that's the way you construct it to get higher order. Okay, so what I mean is, if you have 3 points, you can take the gradient between these two and between these two. So you have 2 equations. You say gradient times delta xp east, delta xp west. So this or this gives you phi, say, delta phi p east or delta phi p west. And in 2D, you can have, you know, if you have a polyhedral, you can have 20 points and you have 2 gradients. And you have a matrix which is 20 cross dot 2 or whatever. So it's heavily overdetermined. But you also can say, I forget about this. Or you can say, I take this minus that or whatever. This is just to indicate that what finite volume does is basically to do this overdetermined matrix and multiply it with the transposed ornament. And that gives you the solution. And that's actually not too far away from a finite difference scheme.
But these equations are always consistent with each other, right? Like there's no, like we can always find a solution.
I'm not too sure actually, but should. I'm not too sure actually. You know, you have some kind of Jacobian inside, and the Jacobian can be an issue, but the Jacobian is for all schemes an issue. What the Jacobian does is it goes to 0 whenever, say you have a 2D situation that ideally looks like that, but then if you turn the second direction in the direction of the first, like that, then there is no way you can distinguish d by d eta and d by d psi. And this means your Jacobian will by all means get singular. And this transformation issue is an issue for all these schemes, I believe. They all rely on this funny transformation because then you invert something and the funny Jacobian occurs, which actually doesn't want you to squeeze lines into each other. For finite volumes, it would mean that your control volume size gets 0. It's also something you don't want.
Is there any other question here? Maybe a question from the online audience? Anybody? Dimitris, did you have a question?
Not really. I think it was very nice, quite dense a little bit, but maybe on a second take we will absorb a bit more. But thanks for a clear and nice presentation.
All right, thank you. I do have another question, if I may. So when you go back to the final equation, this kind of matrix type equation. So how would you? Yes. So basically, that was the last piece. So that's what you then actually simulate, isn't that?
Yeah,
Right?
so this is the main diagonal. This is one of diagonals to the upper and lower. So
Right.
if you only have 3 diagonals for structured money.
And so basically, this equation then needs to be solved. It's nonlinear because is it?
Because
U and rho.
No, we never know the velocity in fluid mechanics.
Right. And so this basically, how is this then solved in practice?
Okay. In practice, you linearize here. You have to linearize because this is a nonlinearity.
Right.
Now, how do you linearize? Well, we can have a course for 2 days to show this. It's not too difficult. But assume you are able to linearize it.
Okay.
This actually means that you are guessing part of the matrix elements on your present knowledge, which means you have to iterate, because if you're guessing, then you solve for the velocity, and then what you guessed is most likely not what you get out of the solution. So you iterate that to convergence. Your next velocity gets then the next guess, and you have to do it again, which is why we usually use iterative solvers that are usually also not too strict in terms of some of the convergences. Why? Because direct solvers is what they use in finite elements, because structures are linear. They don't have the trouble. Their matrix entries are no longer functions of the solutions.
Right.
They can devote a lot of effort to getting the solution, but if we do that, we are putting a lot of effort into getting the solution, which is not the final solution anyway, because it's based on some kind of funny guess.
Right.
And we don't want to, put too much effort into the guess.
Okay. So then.
So then you iterate that to convergence. You also have a right-hand side usually, which is, this case was very simple. There's no right-hand side.
And so the thing to guess is the UP.
Is the velocity. And to some extent, for instance, if you're talking about turbulent flows, you usually have a viscosity. That's here a gamma in this case, but depends on the velocity.
Okay.
Right. Or on blah, 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 blah.
Uh-huh.
Or you do have a density distribution in multi-phase flows, which depends on, and then you update that. So you have multiple also in the sources areas where your unknowns occur, which pushes you into an iterative scheme. And the thing that I outlined before was, how do you do the approximation for this funny angle thing where,
right.
If you do the straight line, you don't even touch the face. This is done by wishful thinking, reality minus wishful thinking. Reality minus wishful thinking occurs on the right-hand side. Both of them need the solution.
Okay.
So that also is something of the iterative process. But the short story is, here you're done, because this is part of your unknown. There's no way you can do fluid mechanics without flow. And if you have flow, you are immediately nonlinear, which brings in trouble.
Okay. And so then basically you start with initial guesses from the previous time step, or?
The initial one is usually homogeneous. Homogeneous, everywhere 1 or 0. Well, 0 is not too good because sometimes you divide by 0, it's not very favorable. So your initial guess is something, and then if you go in time, you take the best for the next time step is, of course, the last solution of the previous time step. So you carry on with the old solution of the previous time step to do the first guess of the next time step.
And so basically this term that you have here, that needs to be turned into zero. So this is in essence an optimization problem. Where, you know, you want
Well,
your
we
choice.
iterated to convert, we don't optimize the initial guess.
So you iterate it to convergence such that rho and u and so on are chosen that this expression here gives zero.
There's no change anymore in terms of the solution of the equation
The
system.
equation system, okay. But that is in a way optimizing.
You can
this
cast
expression.
that into an optimization problem.
Right.
Yes. So you basically optimize the coefficients if you want.
Right, so you could take the modulus of this thing, and that would always be larger than zero, and you optimize it to get to the minimum. To
You
get
can
the,
cast it in.
and that's what nobody does that. I mean, you use these iterative solvers, so they are. I mean, how different
I
are
would
they?
say nobody, you never know what
Never
to do, but it turns out that there's a lot of activity on fast iterative solvers and multi-grid strategies and whatever, you know, comes with that,
Yes,
which is very hard to compete with.
so this has the name of multi-grid solvers essentially.
But, well, you don't need to do, but as I said, there's a lot of activity such as
Yes.
multi-grid solvers and whatever rapid Schur complement solvers and whatever you name it, you know, you're getting it. Actually, some of the equations, I didn't actually come to the biggest challenge. The biggest effort and the biggest challenge is the pressure equation.
Right,
And why is this a challenge? Because you have three equations which say dy by dt and rho is equal minus whatever pressure. And what is Newton? Change of momentum is sum of all forces. Forces can impose on surfaces and magic forces on the volume or mass or whatever. Minus or plus, which is the body force, in this case, minus rho times g. If z goes up, plus d by dx tau ik, and this tau ik is gradient of velocity plus its transpose times finally whatever, you know. Now then you have one more equation, which in incompressible flows and many of the, if you don't go for high-speed aerodynamics or rocket science, usually the velocity, the viscosity, the medium is incompressible. So the density is virtually the same. It comes from mass. The conservation of mass is density times volume. If density is a constant, you conserve volume and not mass. And volume conservation actually is duk by dxk is zero. Well, actually times rho, but it should hold for all values of density. So this is zero. What is the trouble? The trouble is you have three equations to determine the velocity essentially. This is known, this comes with the velocity, so it's also known as some kind of material property. This is actually also known, the density. So what you need to do is you need to find the pressure. The pressure is not known, but you don't have an equation for the pressure. There is no equation for the pressure. There is instead of that a fourth equation, again, for the velocities. And this brings basically, I would say, 80% of the iterative effort or whatever, depends a bit on the problem, is how to get the final pressure. And what people typically do is they take the divergence of this, which gives a Laplace on the pressure and gives, you know, swap that, and due to this is zero. This hopefully is also not contributing, whatever it is. And this contributes to some extent. there's a vortex stretching and whatever other term, but essentially you're having a Poisson equation because there is something that doesn't vanish for the pressure. And some people use this as we do in terms of a pressure correction scheme, some do a pressure projection scheme. Essentially, that's the same. But the trouble is that this equation gives you a matrix which basically has an entry here, an entry there, and a zero here if you have the velocity and the pressure collected. And this is not too good. But there's no way you can avoid this for incompressible flows. And there are tricks which again go towards how to iterate that to convergence. There's the biggest effort is actually in there. In this funny final equation here, this goes down into that, or the combination of the divergence and that. And
So, sorry, one final question, if I may. In this last equation here, the max and the minimum for the upwind is gone. Is that always possible to rewrite this without any max and min
this
functions?
is written without max min because I assumed a certain direction for that part.
Right.
What you have is AP is equal to plus X. Now you have the sum because if you have a control volume, and this is your point P, you have a number of phases. And of course, for each of these phases, you do this operation and then you walk around, so you sum it up. Max M dot F 0. And you might have contributions from diffusion fluxes and time derivatives and whatever, I don't write them up. Now for the neighbor points, here, there, you have plus and not max because for this control each neighbor occurs only once. And if you paid attention, actually you realize that I had a minus here to activate the neighbor if the flow goes from the other side. Now, what is the trouble here? This is actually a very good question. No one asked this question, but I always raise the issue in the lecture. And hardly anyone knows this. And then you see where the experts come from and where not. What is the issue? The issue is there are two golden rules for monotonicity and to make the matrix well-behaving for an iterative solver. And one of the rules for monotonicity is that for making the matrix being dominant is that the sum of these neighbor coefficients is the main diagonal coefficients. If you look at that, it means that if I would sum them, this sum and this sum should be the same. But actually the rule says they should be smaller, or at least one row should be smaller. But if you have a time integrating scheme, you have additional 1 over delta t parts to AP, so that's safe. And if you do relaxation and you have a linearization, which we'll do in the course, then you get this. Right. But let's say it is like that. Is that true?
That they are equal.
Well, essentially, is that they are equal. Is that true? It basically says that what goes in and goes out has to be the same. So if the sum of, say, yellow and the sum of blue is the same, then that's okay. Which, for the ideal, real, and final converged solution, ideal solution is true. But if you start with your initial guess, everything is one, by no means you guarantee that this is true. So for all intermediate steps of your iterative schemes, this is violated. However, if your iteration is requiring that the system delivers to get the iteration convergent to the real solution, you have a problem. Because you can't do it with something that only works for the real solution. You're starting from a guess. It has to work from the guess. And if it has to work for the guess, there is some magic, which hardly anyone knows, that indicates that people in the code migrate a minus into the AP coefficient. So if you say this is minus, then of course this is always strictly the same. It's always strictly conservative. The other thing is actually a bit of an issue also with compilation globally, but you manipulate the equation system. You manipulate it in a way that says for the finally converged situation, this is okay, I can do that, acceptable.
Yes.
Actually, hardly anyone knows, but all serious code do that. Otherwise, they run in trouble. So this points to, this max can also be immediately causes a problem there.
So that means that in general, here the maximum just does not appear because you've assumed a certain
Because I
direction.
assume something, this is how the code looks.
Yes,
And what the code actually does, it only computes this
right.
and then says AP is sum of neighbors. Well, this is what everyone confirms who does the coding, but what people usually don't see that if you do this, you actually do that.
Right.
So this is never computed. And to make sure that the same thing is conservative and always converges and has a appreciable property of the matrix, they don't compute that. They, after gathering all operations on the off diagonals, they take the main diagonal as the sum of the neighbor, and then subsequently say AP is AP plus delta volume over delta t. For instance, the time integration is then supplemented. Because the time integration doesn't work on the neighbors, only works on the main diagonal. But for diffusion and convection, you never do. You always do the neighbors and then collect everything, push it into AP, which means you manipulate.
And so for the neighbors, then you may get no contribution if MF is positive.
Yes, then you have nothing.
Then you
But
have nothing.
at some stage, there must be flow going in. Well, if there's no flow going in, you have nothing.
Okay.
Only diffusion. Diffusion provides all
Yes.
this.
So that means in the code, you always look at the neighbors. If the neighbors give you flow in,
Yeah.
then you count
put
it.
the neighbors,
And if it doesn't, you ignore it.
you ignore it. And then finally, you just add what the neighbors did to yourself.
Right. And so in the end, when you've iterated to convergence, that must be correct.
Yes.
But while you go there, you get some
Not correct, but it's favorable to
get to the right.
to get the converge, or to improve the convergence. Otherwise, you might fail with your convergence because in matrix, and this is not a small detail because the Reynolds number is big and this term is actually contributing by 10 to the 6, 7, 8, 9 times as much as the other terms.
Okay, thanks. Are there any other questions? Well, if not, I don't see any kind of online questions. Then let's thank Thomas again. I think I've done this. And we're going to have coffee now. So when do we continue?
30 minutes.
In 30 minutes at 11:30. So we're having a break, and in 30 minutes we're going to continue. Sorry, I can't offer you coffee through the internet. So we'll be back in about 30 minutes. And I stop recording it now and